Welcome to yet another discussion as part of the IIT PAL program, and for the next few lectures we will consider surface chemistry. Which figures as Unit 5 of NCERT Volume 1, Class 12 Chemistry Series. I am Narayanan Kurur, and I teach in the chemistry department at IIT Delhi. So, if you look at this chapter in the NCERT textbook dealing with surface chemistry, so we have, it says surface chemistry in the title of the chapter, and it has, if you looked carefully, 3 different portions. There is one on adsorption, that is a significantly big section. Then there is a section on catalysis, and a third section, well, more than one section, on colloids. So, the 3 portions that figure in this chapter on surface chemistry primarily are adsorption, catalysis, and colloids. So, if you looked at this chapter and the sections that we have written out here, you get the impression that there is something that is strange about it. What is the connection between adsorption, catalysis, and colloids? And the thing that holds it together is surfaces. So, the first thing that we will try and do is to establish a connection between these 3 fields and surface chemistry, and then later on we will look at each of these 3 topics in detail. So, the first thing to establish is, what is it about surfaces? Anywhere you look around, you look at me, for example, I am a solid object, and I have a surface between my skin, for example, or my body and the atmosphere. So, I have, in this instance, I have a solid, which is my body, or for that matter your body, and the atmosphere around you, which is the gas phase. So, I have here an interface between a solid and a gas. Any object that you look around, you have this solid gas interface. Solid, as we all know, is one state of matter, and gas is another state of matter. So, any time you have a surface between 2 different states of matter, you have an interface or a surface. So, the example that we cited is any body and the atmosphere. So, if you go on like this, what you will find is that you will find an interface between a solid and a liquid. This is something that you will see when you stick your hand into water, for example, or if you have a ship which is riding on the surface of water, you have a solid liquid interface. And then you have a solid solid interface. So, I have represented all these surfaces between the 2 states of matter represented one state and the other state with a slash in between. So, I have a solid interface. This is what, when you have a table like the one that I am sitting at, sitting on the floor, there is an interaction between two solid surfaces. So, the reason that we are able to walk, for example, is because we have the surface of our body, our feet, for example, touching the ground. So, there is a solid interface, for example, the friction which allows us to walk. So, anytime you have two solid objects which are in touch with each other, there is an interface. So, this is the interface that you have, or surface, between two different states of matter, between two different states of matter, or between two different phases. Similarly, I could have, I am not talking about liquid solid, because if I have a solid liquid interface, obviously I would have a liquid surface interface, the only difference being which is the one that we are giving importance to. You could then have also a liquid gas interface. Any time you have a container in which you have a liquid in contact with the atmosphere, then I have a liquid gas interface. So, the ocean, for example, out there is the ocean, there you have water surface in interaction with the atmosphere, that is a liquid gas interface. There are also the liquid interface, and if I had written it in sequence, I should have come before this. There you have liquid interface. For example, you have oil dispersed in water, or dispersed or on top of water, oil dispersed in water, that would be a liquid interface. So, you have solid gas, solid liquid, solid liquid liquid gas, but you do not have the gas interface, because gases mix in all proportion. So, I do not have an interface when I have a mixture of gases. So, the atmosphere itself is a perfect example of that. I have a mixture of gases and there is only one phase. I do not have an interface between the different components of atmosphere. So, this is the kind of surfaces that we are looking at. We have an interface any time we have two phases that are in touch with each other, right. And so, surfaces are some things that you are going to see any time you see anything pretty much around you. So, then what is this importance? So, now that we have established that surfaces are important everywhere, what we now need to look at is what is it about colloids and about catalysis, and how is it connected with surfaces before we study this chapter itself. And I will illustrate this with an example as to the importance of surfaces and how then it is connected with catalysis and colloids, etc. I will discuss this as we go along. Let us take a cube which is 1 centimeter in length. I take a cube which is 1 centimeter in length. If I now compute the surface area of the cube, and the surface area is the area of each surface, which is 1 square centimeter, 1 centimeter along a length and 1 centimeter along a breadth or height. So, that gives me 1 square centimeter, and I have 6 faces leading to a surface area of 6 square centimeter. Now, let us take this cube that we have got here and divide this such that I make a lot of small cubes, each cube which is 1 millimeter by side. So, I take this cube that I have got and divide it in such a way that each length is now 1 millimeter, which means that what I have taken is taken this cube and divided it like this first. so that I get 10 different slabs. So, I divide one, take a small slab which is 1 millimeter in width. This is 1 millimeter like this, and then further divide it like that. If I did this, each cube now I would have of length. So, divide the cube into many cubes of 1 millimeter side. The side length is 1 millimeter. Now, if you looked at the surface area of each of the cubes that are formed is going to be 1 millimeter square, and I have now, because I have divided them into 1 millimeter length, I will have 1000 times 6 faces. So, each cube has now 6 millimeters square. It appears that the surface area is smaller, but I have now the total surface area. I have 1000 such cubes. So, the total surface area, if you thought about, is 60 cm square. And if you want to do it consistently in units in the MKS or the SI system, so this is 6 centimeters square into 10 to the minus 4 meters square per cm square. That will give me 6 times 10 to the minus 4 meters square. If I go down, it is 1 millimeter length, it will be 60 cm square times 10 to the minus 4 meters square over cm square. That will give me 6 times 10 to the minus 3 meters square. So, if I took a cube of 1 centimeter length and then divided it into lots of small cubes of 1 square millimeter, my total surface area has gone up by a factor of 10. We started off with 6 cm square, and after doing this we have gone up to 60 cm square. You could now think of what will happen. Imagine now if I take each cube of 1 millimeter and subdivide it even further, and I could go on. So, I take this and I go down to, let us imagine that I go down to 1 micron, which is 10 to the minus 6 meter, or 10 to the minus 4 centimeters, which means that I have gone from 1 millimeter 3 orders of magnitude down. If I did this, each cube would now have a surface area of 10 to the minus 6 meter is this length. So, 10 to the minus 6 meters into 10 to the minus 6 meters into 6 faces. That is the surface area of each cube that we have got. But in going from 10 to the minus 1 centimeter down to 10 to the minus 4 centimeter, or from 10 to the minus 2 meters to 10 to the minus 6 meters, I have gone down by 4 units. So, I would then have to multiply it by 10 to the 12 such cubes that I have got. So, this is number of cubes is 10 to the 12. I have started with 10 to the 0, let us imagine 10 to the 0, that is 1 meter, or 10 to the minus 2, which is 1 centimeter, and I have went down to 10 to the minus 6 meters. So, that is a factor of 4. So, if I go, this is 4 orders of magnitude. And if I go down by 4 orders of magnitude, that is cut the cube into such small things, what will happen is I will make 10 to the 4 times 10 to the 4 times 10 to the 4 cubes, which is why I get this 10 to the 12. And now what you've got is essentially 6 meter square surface area. 10 to the minus 6 meter is 1 micron. So nowadays people are interested in things which are called nanotechnology. You might be aware of it already. If you aren't, it is something dealing with dimensions which are of the order of 10 to the minus 9 meters. So if I went down even further, this happens to be 1 micron is 1000 nanometers. 1000 into 10 to the minus 9 meter is 1 micron. So if I went from 1000 nanometers down to 10 nanometers, so I now make cubes which are 10 nanometers across the side. So I have gone down another factor of 2. So I go from 6 meters square, and the total surface area then becomes 6 meters square into 100, the total number of divisions that I have got. So I have got 600 square meters. And what am I trying to illustrate with this calculation? What I am trying to illustrate with this calculation is that as the size of the object keeps going down, the surface area keeps increasing. So if I took a cube which was 1 centimeter in length and then went down to 10 to the minus 8 meter, which is 10 nanometers, the surface area went from 6 square centimeter to 600 square meter. And to give you a sense of 600 square meters, this is about the area of a tennis court. Approximately. So what this means is that if I took a small cube 1 centimeter inside and then divided it such that each cube now becomes 10 nanometers, and if I laid them on the floor, I could pretty much cover all the tennis court. So the surface area has gone extensively when I went down from 1 centimeter down to 10 nanometers. So the moral of the story is that smaller the size of the object, larger is the surface area. And now you can establish the connection between what we have. We have on the one side catalysis, and we look primarily at heterogeneous catalysis, and we will come to what heterogeneous catalysis is in a moment. Anytime you have catalysis, for example, something that you and I have encountered, if you look at any automobile, a car that has been made in India in the recent past, if you look at the back of the car, you will see stickers which says BS2, BS3, etc., and so on. So if you look at the back of your car that you have, or any car that is passing by, you will see these notations there which says Bharat stage 2, Bharat stage 3, etc. And what these have are catalysts, and these catalysts are solids. And if you know what happens in a car, for example, is that you burn petrol. And when you burn petrol, what you are going to get is, in addition to carbon dioxide and water, you will get oxide of carbon, which is carbon monoxide other than carbon dioxide. You will get oxides of nitrogen, which are called NOxes, and you will have unburnt hydrocarbons. Now, we all know, thanks to the media and other educational things that you have seen, these gases, when they come out to the atmosphere, are going to ruin it for us and for everybody who comes to this planet after us. So, we have to ensure that what we put out into the open does not contain these things. So, this is what you get from the exhaust of your car if you did not do anything. So, to improve what you put out in the environment, what you do is you take this exhaust that you get and you put it through what is called a catalytic converter. You put the exhaust gases through a catalytic converter, which is a solid, and this fits into the bottom of your car. You have these exhaust gases coming through at high temperature, and they are flowing through at high speeds. You take this, you put it into this catalytic converter, which is a solid, and these gases then get converted into harmless, well, or less harmful chemicals. So, the carbon monoxide gets converted into carbon dioxide, the NOx's, which is various oxides of nitrogen, get converted into nitrogen, and the carbon hydrogen unburnt fuel that exists is converted into carbon dioxide and water. So, you take the harmful gases, put it through a solid catalyst, and then convert it into gases which are less harmful. So, this is a solid catalyst. The exhaust that comes through is a gas. So, and we have already seen, if I imagine that I take X amount of the catalyst, if I want to have it efficiently converted, rather than have all this in one single block of catalyst, what I would do is try and divide the catalyst into small cubes such that the surface area is increased. So, when the gas comes through, it will stick onto this catalyst and get converted into something else. So, here for example, you have a solid gas interface, and what we are saying is the solid, which is the catalyst that we are using here, has to be of such small dimension such that its surface area is large. So, more gas could get converted from the harmful ones to the less harmful ones as the gas comes through this. So, the gas is flying through here, here is a catalyst, and it gets converted into harmless or less harmful things and comes out here. What I am saying is, if I have a big solid object of catalyst here, that is going to be less efficient than if I took this and broke it up into small pieces. So, all the gas is spread out now. So, the gases can then more efficiently be converted. So, here is an example of a solid gas interface working in catalysis. So, the moral of the story from this example, that what I am trying to illustrate is that if you want catalysis and if you are doing it heterogeneously, which means that the reaction medium is different from the reaction medium, in this case gases, the reaction is happening in a different medium from where the reactants are. So, it is happening on the solid surface. So, that is why it is called heterogeneous. You take any example of importance in the chemical industry, any chemical industry, and the biggest industrial chemical that we have is sulfuric acid. And this reaction to produce sulfuric acid, for example, happens through the use of a heterogeneous catalyst. So, any chemical industry you are looking at, sulfuric acid will involve a heterogeneous catalyst. Ammonia by the Haber-Bosch process, another chemical of very great importance, also produced using a catalyst. So, anytime you have a catalyst, you are going to have typically a solid, gas. So, heterogeneous catalyst, because of economics, it is better to use heterogeneous catalyst. And so, you are going to reduce the size of the catalyst such that you have large surface area. So, anytime you have catalyst, you are going to have surface phenomenon. Surface phenomenon becomes very important. So, that is one reason why catalysis figures in this chapter. The other thing that we are going to look at, surface phenomena anyway, we are going to look at that. The other thing that you have is colloids. Colloids again is what we do is we are going to disperse. So, for example, anything of paints, pigments, food are various examples of colloids, where the particle size, so you have one compound which is dispersed in another material. So, you would have a dispersed medium. For example, if you have paints, you have some coloring dye which is put into a solvent. So, you have a liquid dispersed in another liquid, or you have food material where you have solid objects dispersed in a liquid. Even milk, for example, is in some sense a colloid, because you have all sorts of particles dispersed in a water kind of medium. So, anytime you have colloids, you have particles of small size, relatively small size. And when you have particles of small size, what we have already concluded is we have high surface area. And when you have high surface area, so we are going to look at surface phenomena. So, the thing that holds us together in this chapter is, as the size of the particles decreases, we are going to have more and more importance of surface phenomena. So, that is the thing that holds these three things together: catalysis, colloids, all related to surface phenomena. So, what we are going to look at is surface phenomena, and everything, most of what you see in industry, etc., has great technological importance. And if you look at that chapter in the book, there are lots and lots of examples that they give which illustrates the importance of catalysis and colloids in everyday lives. So, we won't worry too much about where its applications are, except to overall give you an overview of where it could be. But finally, the driving force is that everyday lives are affected by phenomena which involves either colloids or catalysis, all of which involve materials with high surface area. There is another way of looking at this same thing. Imagine that I have a compound whose length is h, any material, call it silver bromide, something, anything whose, I am saying its dimension. So, I am saying let us imagine that I have a cube, that silver bromide is a cube. It is very, very qualitative, but nonetheless it is illustrative. So, I am saying that any particle that we look at can be represented by a cube of dimension h. So, I am saying first of all that the particle is a cube, that a molecule is a cube and the dimension is h. So, its volume is going to be h cube. And imagine that each of these silver bromide particles makes up a cube of length L. So, a lot of these cubes are then put together and its dimension becomes L. And by the same argument that you wrote out, that we wrote out just a while ago, you can figure out that the fraction of surface molecules approximately, very qualitatively, the fraction of surface molecules is given by 6 times approximately, I am taking it to be cube, this ratio of H over L. So, this will tell me if I have a cube of length L composed of small cubes of dimension H, this will tell me the amount fraction of surface molecules. And if you have dimensions which are macroscopic, so if length is a macroscopic length, that is of the order of centimeters or so, then the number of surface fraction of surface molecules is typically going to be 1 in 10 million or so. For reasonable molecules, well, let us say whose volume is say 30 cc's per mole, if I took this, that is a typical molecule, then what you are going to see, and H, if you looked at this, if you wrote it as a cube, then H would work out to be less than 1 nanometer. What we are saying is the number of surface atoms is, if you have 10 million atoms, you have 1 surface atom, which means that the importance of this surface atom, so this is the number of surface atoms in this total number of atoms or molecules. So, the importance of the surface atom 1 in 10 million is relatively small. Now, what we are saying is, if I drop this length, that is, if I break this big cube of 1 centimeter and make it into smaller and smaller cubes, what you will quickly find is that the number of surface atoms increases dramatically. So, the fraction increases, and when you reach about 10 nanometers, you will find that you have 1 surface atom or molecule for every 4 or 5 molecules, which means that 25% of the molecules in a cube of 10 nanometers is made up of surface molecules. So, you now realize the importance of a surface molecule as the size drops. So, we have now given 2 instances where we see that as you 2 instances, 2 illustrative examples you might want to call it, where as you decrease the size of the object, the surface area increases, that is one illustration we gave, and the other we are saying is that as the size decreases, the fraction of surface molecules increases. Now, why is surface molecules important and why do they behave differently? Let us look at that for a moment. So, imagine that I have a liquid or a solid surface like this. So, this is my surface. So, these are the surface atoms or molecules, whether it is a solid or not, the way it is represented, it might look as a solid. So, let us imagine that I have this solid and I have this pattern like this. So, that is my solid here. This is my surface layer. And if I look at the surface layer as opposed to a bulk layer like this somewhere, this is a bulk. And a molecule in the bulk, for example, this one here, has all its valencies satisfied pretty much, because it is surrounded by molecules on all sides. Its bonding is essentially completely satisfied. On the other hand, a molecule on the surface here has bonds with the ones below it, but has essentially free things up on top. So, there is unsatisfied valency of the surface atom, as a result of which these surface atoms are looking for ways to somehow satisfy the valency. And this is the reason why, well, the fundamental reason why surface atoms or surfaces behave differently. So, anytime something comes in, this would like to satisfy its valence by grabbing the thing that comes in front of it. And so, you can imagine why surfaces behave differently. So, the first thing that we will do is to look at some of the phenomena that happens in surfaces. And most of what we will do is look at the solid gas surface. You could have other things like the liquid gas surface, where people would be interested in surface tension and things of that nature, but what we would primarily be interested in is the solid gas interface. And the reason for that is not too hard to understand, because finally we want to also connect it with catalysis involving heterogeneous catalysts. So, we want to look at catalysis, most of which involve solid catalysts. So, we are going to look at the solid gas interface. So, if you have a solid, if you looked at any electronics goods that you have bought in recent times, take whether you take a mobile telephone, you have taken anything that you have bought, a computer, anything that you have got, if you looked inside the package, you would find a very small piece of white thing which comes in a white polythene cover or some other polyvinyl cover. And if you looked at that, that white thing in any electronics goods, electronics packaging, will have some white packet, and that white packet happens to have a silica gel. And these silica gel, if you do it carefully without doing any damage, you open it, and what you will see are, you will see particles, small particles, and what they do is to pick up the water, the atmosphere. So, if you have moisture, these electronics goods, especially those which have optics, tend to go bad. So, to avoid this, they put this silica gel in the packaging, so that it takes away the water, and that is the kind of thing that we are interested in studying. So, anytime, the other thing that you have, especially if you live in cities, most of you would have water purifiers at home, and sometimes the mechanic would come to clean it, and if you happen to look at what is there in that, one of the things that you will find is a black, very, very small particulate matter, and that is activated charcoal. And what does activated charcoal do in this water filter? So, most of us probably are using water filters, especially if you live in the city. You could use it even if you weren't. And you take this activated charcoal, which is a black thing. What you get is from burning wood essentially, and you get it of particular size, you activate it in some way, and you put it into water. Any particulate matter that you have, let us imagine that you have dirty water, and you put this activated charcoal at the bottom, and you will find that as time goes, the color of the water becomes cleaner, and the reason is that you have adsorption, which means that the activated charcoal, which has small particles, are going to pick up these particles which are floating on the liquid on top of it, and they settle in the activated charcoal, which is the reason why that periodically in your water purifying systems you have to change this activated charcoal on a regular basis if you have to make it useful. So, in all of this, what is happening is a process which is called as adsorption. I will spell this out for you. It is called adsorption. So, if you have a surface, imagine this surface, and I am not drawing the things that are there at the bottom. What is happening is, and let us imagine that I have some water molecule or something like this. So, this is silica, think about it. So, water comes and binds to this. Okay. So, I have water molecules and they bind to the surface. This is called adsorption. Surface where the molecules get bound to the surface. Contrast this with what something that you have come across already, which is absorption. The difference between adsorption and absorption is that adsorption happens on the surface. It is a surface phenomenon, whereas absorption is that these particles will go and will sit. So, water will go and sit inside. So, if I have surfaces, should have drawn it in red. So, if I draw it in red, these are my molecules of the material, for example, activated charcoal or silica, and the water molecules go inside, go buried into the solid. That would constitute absorption, whereas when it happens on the surface, it happens to be adsorption. And the reason for this is, we said, unsatisfied valences, right. So, this is happening because of unsatisfied valence of surface atoms or molecules. So, the first thing that we differentiate is adsorption from absorption, and any time you have a solid, it is going to be macroscopic, which means that it is not very, very small. Even 10 nanometers has a large number of atoms. So, any time you have a solid like this, you pretty much have adsorption happening along with absorption. Both of this will happen. But when the particle size becomes small, we have already established that the number of surface molecules and the surface area, fraction of surface molecules become large, the surface area becomes big, the adsorption phenomenon becomes more important, which is why we will now primarily concern ourselves with adsorption. And we have already said that catalysts involve materials of large surface area. So, when the gas comes through, you are going to have adsorption. So, when you have gas masks, people wearing gas masks, for example, that if you live in Delhi like I do, then you will find that many people wear masks when the pollution in the city becomes too high, and they also involve this thing of adsorption, which is why there is no point in wearing the same mask over and over again, because once what happens is it gets coated on the surface of the mask, and unless you clean it and get rid of it, the efficiency drops. So, all masks that are used have a definite lifetime, the same as the activated charcoal in your water purifier having to be cleaned regularly. It is the same thing with your face mask. So, in all of this, because of the high surface area, adsorption is a predominant thing. Absorption is happening side by side. Please understand this. This is important to realize. It is not as if absorption is not happening. Okay. The other thing that we have to look at is that any time you have adsorption, we already said that what is happening is unsatisfied valences being satisfied. So, if I have a surface like this, whether it is activated charcoal or silica or anything else. So, I have some molecule of a different color, let me call it, comes and binds to the surface. It will come close, and what we are saying is when it happens on the surface, this is adsorption. So, now this valence is satisfied and a small bond is formed. It may not be, well, it may or may not be as strong as a bond that exists between two atoms in a molecule, but certainly there is a bond that is formed. And one of the characteristics is when a bond is formed, we are going to heat is liberated. So, heat is liberated on bond formation. This is something that we all know, and because on adsorption there is a small bond formation, adsorption is always accompanied by liberation of heat. And in technical terms, what we mean is that delta H, that is the enthalpy of adsorption, is negative. That is what this means. We are putting it in technical terms. Delta H of adsorption, that is the enthalpy of adsorption, so any time a molecule gets adsorbed on any surface, heat is going to get liberated. The stronger the bond, the more heat that would get liberated. The other thing that happens is that because a molecule, so and we are all in all of these cases we are looking at the solid gas interface. So, imagine that I have a gas that is here and I have a surface here, it gets adsorbed. Obviously, the entropy of the gas decreases. The entropy of the gas decreases when adsorption happens. So, the delta S of adsorption is also going to be less than 0. And we know from our thermodynamics that if you want something to happen, that the delta G of adsorption has to be less than 0, and delta G of adsorption is delta H of adsorption minus T delta S of adsorption. This is negative. If this had been positive, we know that at all temperatures you would always get this to be less than 0. However, what we are seeing here, so what I am saying is, if delta H were of adsorption were negative and this were positive, this is a hypothetical situation. If delta H is negative and this is positive, at any temperature this would be a process that is thermodynamically feasible. However, in this case delta S is negative, delta H is negative because we said that bond is being formed. This is because this is negative because gas which is free to move becomes fixed to the surface, as a result of which the system of the gas has a decreased entropy after. So, we are looking at gas plus solid going to Gs. So, if you looked at it from the gas perspective, the degrees of freedom that exists when it is in the gas phase has come down when it is bound on the surface, and when that happens the entropy goes down. So, in reality delta S is also negative, and now you have this is a negative quantity, this is also a negative quantity. So, there are only some temperatures at which this delta G of adsorption is going to be negative. There will be some temperatures where this will outweigh this, and in which case you will not have adsorption. So, there is an interplay between two quantities such that you are going to have adsorption, and that will only happen at a particular temperature. Okay. So, now what we will need to look at is what happens when a gas comes to the surface. So, if you have a surface like this, what we are saying is, and you have gas molecules, call it red dots, let us imagine, and we have a large pressure on top of this. All this is put into a box, call it, and what we are saying, if we let this be, after some time, if you looked at it, some of the molecules would be adsorbed, some molecules are adsorbed pretty much randomly. So, I started with 5 and 6, 11, 4 of them got adsorbed, and so 7 would remain. So, if you now stick a barometer or a manometer on top of this, you fill it with mercury or whatever, some measuring liquid, what we are going to say is that the pressure that you see after the adsorption is going to be lower than what you started off with. This is something that you will see when adsorption happens. And what we are going to now try and do is to relate, and this is some amount of the surface is now covered with the gas. So, what we are now going to do in the next class is to look at how the surface coverage is going to be related to the pressure on top. So, we are going to relate the surface coverage, and there is a relationship between the surface coverage and the pressure on top. What we will try and do is to relate the surface coverage. So, in this case we have 6 surface molecules of the solid, and we have 4 covered, which means that the surface coverage is 4 over 6. We are going to relate the surface coverage to the pressure of the gas above the surface. So, in the next class what we will do is to look at the surface coverage as a function of the gas pressure. If you have a solid gas interface, then it is the surface, the pressure on top of it. If you have a liquid on top of a solid, then it will be the concentration of the liquid which is on top. So, we will relate the surface coverage to the pressure or the concentration. This is of great importance, because you can imagine that if I have a catalytic reaction, and if I have, let us say, your gases coming out of the exhaust after burning, and if it goes on, sits on the catalyst, the pressure on top will determine how much is covered, and how much of covered is important, because the reaction that happens is going to be related to how much surface coverage we have. So, understanding this is of great importance, and we will take this up in the next class. But to recap quickly, what we have done today is to introduce to you surfaces with the idea that we will need to understand surfaces and adsorption phenomena and things like that related to surfaces, because finally we would like to understand catalysis and colloids, emulsions, etc., because a lot of these things have great technological and other importance in our everyday lives. With that, we will conclude today. Thank you very much.